Another real-life phenomenon that can be modeled with the law of exponential growth and decay is the decay of radioactive substances. The half-life is the time required for half of the amount of a radioactive substance to decay. So let's look at example 3. The half-life of radioactive potassium is given to be 1.3 billion years. So that means it takes 1.3 billion years for half of the original amount of the potassium to decay. If 10 grams are present now, how much will be present in 10 years? So we're going to first fill in our exponential growth, or in this case decay, our general model. A of t equals a sub 0 times e to the kt. Okay, so when we're given half-life, half-life is going to allow us to solve for that k. Remember, if we're going to use this model, we have to be able to fill in that k, that growth rate, or in this case, it would be negative growth, the rate of decay in this case. So half-life is giving us information to solve for k. So if we use a generic amount, original amount of a sub 0, then half of that would be half of a sub 0. So if I substitute in 1/2 of a0 equals a0 times e to the k, and they told us that that half-life is 1.3 billion years. So for the t here, I'm going to fill in, and I'm going to write that 1.3 times 10 to the 9th for that billion, because we know 1.3 billion, that would be 1,300,000,000. So rather than having to write that out, we'll use our scientific notation. This is a good example of why we want to use, why scientific notation can be useful. So now we have enough information in here to solve for k, because we can see that the a sub zeros are going to divide out. And this is similar to when we did the compound interest and we were asking for how long it would take for an investment to double. This is a similar idea. We're just using any generic amount a sub 0, and then we'll just have half of it over here. So now on the left side I'll have a half, and that's going to equal e to the 1.3 times 10 to the 9th k. So now if I want to solve for that k, I've got to get that variable out of the exponent, so I know I can use logarithms to do that. So I'll take natural log of a half, so I'll convert this into logarithmic form, and that's going to equal my 1.3 times 10 to the 9th k. And then to get that k by itself, we'll just divide by that 1.3 times 10 to the 9th. So my k is going to be natural log, and I'll write this fraction as a decimal here just to keep this a little neater, natural log of 0.5 over 1.3 times 10 to the 9th. So if we want to enter into our calculator to approximate this, so we'll have natural log 0.5. And now I want to divide by. Now, if you guys are familiar with this EE button, this is a shortcut for scientific notation. So I'm going to write 1.3 and then EE. So that's saying times 10 raised to the power of 9. So this will give me negative 5.33. I'll round that to about negative 5.3. And again, here's that E, that shortcut, which is a way of saying times 10 to the power of negative 10. So I'm going to write in here my K is approximately negative 5.3 times 10 to the negative 10. So now I can take this K value and substitute it back in, because if we're going to use an exponential growth or decay model, we have to know what K is. So if I fill that in, I'm going to have A of t equals A sub 0 times E, and now we'll fill in our K. So negative 5.3 times 10 to the negative 10 t. Okay, so now Now that we have a model we can use, let's look at the information that we need to find here. They're telling us that 10 grams are present now, so we can look at that as the original amount. So now that's our A sub 0. Actually be here. Our 10 is our A sub 0. And they're asking us how much will be present in 100 years. So if we fill in our 10, so we'll have A of t equals 10 for my A sub 0 times e to the negative 5.3 times 10 to the negative 10 t. Now I've got the complete model filled in. Everything's filled in except t and a, of course. So now if we want to know how much will be present in 100 years, I just need to find a when t is 100. So I'm going to find a of 100. So I'll have 10 times e to the negative 5.3 times 10 to the negative 10, and I'll fill in here for my t, my 100. Now, when we enter this into the calculator, we want to be careful with that exponent. So we'll type in 10 times e to the power of, now here we want our negative 5.3. We'll use our EE for our scientific notation, so that's times 10 to the power of, and we'll put our negative 10. And then we need to multiply this by 100. So that entire exponent is enclosed in parentheses. Okay, so now we've got 9.9999947. So this is a lot of nines here. So you can see that's essentially, we would most often round that to 10. But because we're talking about this radioactive decay, which we know it's going to take 1.3 billion years for half of it to decay, this is a significant difference from the original amount of 10 to this. So I'm going to include all of those decimal places here. So that's approximately 9 point, and then we had 1, 2, 3, 4, 5, 6 nines, and then the 4, 7. And we're talking about radioactive potassium in grams. So we would have 9.9999947 grams after 100 years. So essentially, there's negligible decay, is what that's saying, after 100 years. But again, that makes sense if it takes 1.3 billion years for half of it to decay. So then let's see what would happen after 1,000 years. So now we want to know how much would be present in 1,000 years. So if we put in a 1,000 for our t, we want a of 1,000. So that's going to be 10 times e to the negative 5.3 times 10 to the negative 10 times 1,000. And if we enter this into the calculator, and we can hit second enter just to repeat that same entry, and we can just change that 100 to 1,000. So now, again, very negligible difference here as well, but now we've only got 1, 2, 3, 4, 5 nines after the decimal point instead of 6 here. So we can see that there is, again, very, very slight, but a slight decrease in the amount here of the radioactive potassium. So we will have our 9.12345 nines, and then that 47 grams after 1,000 years.